Hello everyone. In this video we will talk about sequences and sums. So we'll start with a brief recap of sequences. So remember, a sequence is a list of numbers and we usually enumerate it like A1, A2, A3, and so on. And so we're going to just talk again a little bit about closed form and recursive forms. So first, consider the example of just 1, 4, 9, 16, 25, etc. So this is one where if you have the options between a closed form, one which depends, writing the nth term depending only on n, is probably a little bit easier than a recursive form, but let's just note some patterns here. So one, what do we notice? These are all perfect squares, right? So that seems to be important. But if you're also looking at how to get from term to term, we notice this, we're adding 3, then we're adding 5, then we're adding 7, then we're adding 9, and if you keep going, you imagine that that pattern is probably going to continue. So for our closed form here, it's rather simple. We just noted these are perfect squares, and they associate exactly with the term with n, right? So A1 is 1 squared, A2 is 2 squared, A3 is 3 squared, and so on. And so our closed form is AN is n squared. Now, a recursive formula is going to be a little bit more challenging here. So again, we noted that we keep adding odd numbers that go up to the next odd number each time, right? So clearly, we know that the first number is 1. And then how do we get from 1 to the next? So let's look at a couple of examples here. So I want you to notice that A2 is 1, or the previous term, plus 3, which is 2 times 2 minus 1. A3 is then, so we start with 4, the previous term, plus 5, which we can write as 2 times 3 minus 1. And we start to see here, right, 2, 3, let's do one more just to make sure. So A4 is 16, and this is 9 plus 7, and 7 is 2 times 4 minus 1. And so again, we see this. So what's the general pattern here? So again, A1 is 1, and AN here is our AN minus 1, right? We're taking the previous term to start plus 2n minus 1, okay? So these two together gives us our recursive formula. All right, so we'll do one more example here. So the Fibonacci sequence is a very famous one. So this is also a good example because we'll see it actually has a more interesting recursive form and that it depends on more than just the previous term. And also has a very difficult closed form. So let's write out a few terms. So you go 1, 1, 2, 3, 5, 8, 13, 21, and so on. So take a second and see if you notice a pattern. So hopefully you saw that, okay, 1 plus 1 gives you 2. 1 plus 2 gives you 3. 2 plus 3 gives you 5. 3 plus 5 gives you 8, and it keeps going like that. So how can we express this with a recursive formula? Well, we're adding up the two previous terms. So it seems like in general, our AN depends on AN minus 1 and AN minus 2, right? These are exactly the two previous terms. But of course, this doesn't work for the first two terms. And so, before we've just kind of had the first term written. Here we actually need the first two because this only starts working at 3, right? Because we need A1 and A2. So A1 is 1 and A2 is 1. And so these three things together gives us our recursive formula. And so our closed form actually looks like this, which is a really nasty expression, and obviously not a very intuitive one as well. And so this is one where the recursive formula is strongly preferable, right? It just says add up the two previous terms, whereas the closed form is hard to come up with and honestly not that fun to compute even once you know it. All right, so here's your first exercise to kind of practice this. So for the first one, I give you the sequence and I want you to write the closed form and recursive formula for this one. Both of those should be pretty doable. And then for the second, I have written the recursive formula to define a sequence, and I want you to write the first 5 terms. So basically, I want you to focus on translating this so that you can figure out what A3, A4, and A5 are here. Okay, so next we're going to look at sums, and by this I just mean adding up terms in a sequence. So here I'm actually going to change the subscript, but it doesn't really change anything at all. So we'll call the sequence AI, where I is greater than or equal to 1. This tends to just kind of be I is the index usually for sums, but it doesn't really matter. And again, this is the same thing, right? Just A1, A2, A3. We're just using I instead of in there. So if I want the sum of the first n terms of this sequence, well, that would just mean I add up A1 plus A2 plus A3 plus A4 all the way up until I hit AN. But this is kind of lengthy notation, and so how we will usually write this is using our capital sigma here, and write I equals 1 to n of AI. So this is what we call sigma notation for obvious reasons. And all this is saying is exactly what's above. So the I equals 1 here, I is your counter, your step counter, if you will. I equals 1 on the bottom says start at 1. And then the n on top says end at n. So for example, we could look at the sum from I equals 3 to 6, for instance, of just the sequence I. And so we start at 3, then we plug in I equals 4, plug in I equals 5, and plug in I equals 6, and the sigma says we're adding all of these terms up. And so this would just be, right, 7, 12, 18. Okay? All right, so we're going to do a couple of examples here, going kind of both ways. So the first one, we're going to start with sigma notation and then interpret this. So what does this mean? Right, so again, we start with 2. So we get 1 over 2. Then we add up the next one, and we're going until 20, right? So it's 1/2 plus 1/3. Then I is 4, so 1/4, all the way up until we get 1/20th. And that's what this sum represents. And then for this second one, right, we want to express this in sigma notation. So first of all, what do we notice about these terms? Again, these are all perfect squares again, right? But how do we represent it? Because we're not starting with 1 here. So you could say I squared, starting at 3 and then going up to 7 squared. Or you could actually start it at 1 if you like, but then your inside has to become I plus 2, right? So then when you plug in I equals 1, you start with 3 squared. And here, right, you want to end with 49, which is 7 squared. So I would be 5, because 5 plus 2 is 7. And so this is something that's important to note, that you can have different indexing giving you the same sum. Okay, so this is definitely possible. So you don't have unique answers in this case. And for your second exercise, I want you to write this sum, so it does stop hard at 40, in sigma notation. And again, just like the previous example, there's not a unique answer to this. All right, thank you for watching.